Today we will be discussing some interesting problems in permutations and combinations. And the first question is the number of ways of distributing 3 identical physics books and 3 identical mathematics books among 3 students such that each student gets at least one book is 50 plus k, where k is single digit number. Then we need to find value of this k. Now what we'll do is first we'll distribute 3 identical physics books among 3 children without any constraint. So these 3 identical books can be distributed in 3 children in x1 plus x2 plus x3 equals 3 ways, where x1, x2 and x3 are non-negative integers. Now number of non-negative integral solutions of this equation is given by n plus r minus 1 c r minus 1, which is 5c2, and that is 10. So these 3 books, they can be distributed among 3 children in 10 ways. In the same way, 3 mathematics identical books can be distributed among them in again 10 ways. So total number of ways in which these 6 books can be distributed among these 3 children is simply 10 into 10, which is 100 ways. Now here we have a condition that each student must get at least one book. So from the total we have to remove all those cases where at least one child doesn't get any book. So what we'll do is we'll use inclusion and exclusion. So at least one child doesn't get any book. It is given by this n, A union B union C, and it will be this summation NA minus summation NA intersection B and plus N A intersection B intersection C. Now A is this event that this first student, say A, he doesn't get any book. So if A doesn't get any book, then all the 3 books will be distributed among B and C. Now total number of ways of distributing these 3 physics books among B and C is n plus r minus 1 c r minus 1, which is nothing but 4. 3 physics books can be distributed among B and C in simply 4 ways. In the same way, 3 maths books, they can be distributed in again 4 ways. So it will be 4 into 4. Now if the books are distributed among A and C, it will be again 16, and in A and B also it will be 16. So it will be 3c1 into 4 into 4 minus, now taken 2 at a time. So this is 3c2. Now books are not distributed to A and books are not distributed to B. So there is only one way. So it will be simply 1 into 1 and then plus and A intersection B intersection C. So no book is given to A, B or C. So this is not possible. So total number of ways in which at least one child doesn't get any book is 16 into 3, 48 minus 3, which is 45. Now from the total, we have to remove all these cases, and then we'll get all the ways in which we can distribute these books so that each student gets at least one book, and they'll be given by 100 minus 45, and that is simply 55. So answer to this value 55. Now this is 50 plus k, so it will be simply 50 plus 5. So value of k here is simply 5, and that is the answer to this question. Now here the question is, we need to find number of positive integral solutions of x plus y plus z equals 10, where x, y and z are unequal, and it is 20 plus k. We need to find value of k. Now first we will find total number of positive integral solutions of this equation, and it is given by n minus 1c r minus 1, which is nothing but 9c2, and 9c2 is nothing but 36. Now from these total cases, we have to remove all these cases. The variables may be equal. So taking this first case, if x equals y equals z, we'll get 3x equals 10, and we won't get any integral solution in it. Now we'll take the second case where x is equal to y, but it is unequal to z. Now we can write this as 2x plus z, and it'll be equal to 10. Now here this variable x, it can take the value from 1 to 4. So value of x can be 1, 2, 3 and 4. Now if we take x as 1, we'll get z as 8, then 6, then 4, and z equals 2. So we'll have 4 such cases. Now we'll have 2 more cases when y equals z and when x equals z. So it will be simply 3 into 4, which is 12 cases. So from these 36 cases, we have to remove these 12 cases. Then we'll get number of positive integral solutions where x, y, and z are unequal. So total number of positive integral solutions will be simply 36 minus 12, and which is 24, and it is nothing but 20 plus 4. Value of k here is simply 4, and that is the answer to this question. Now here the question is, the total number of ways of selecting 5 letters of word independent is x, then sum of digits of x is. Now we are given this word independent, and this word independent has 3 e's, 3 n's, 2 d's, and then 1 I, 1 P, and 1 T. That is 6, 10, and 1, 11 letters. So this is 4 and 4, 8, and 3, 11. Now we have to find number of ways of selecting 5 letters from it. Now this is selection when the objects may be distinct or identical. So what we'll do is we'll write all possible cases. So possible cases can be this first one where we'll have 3 alike and 2 alike letters. This second case could be when we have 3 alike and 2 distinct letters. This third one is 2 alike and 1 distinct. Fourth one is 2 alike and 3 distinct. And finally, this fifth case where we'll have all 5 distinct letters. Now we have to find number of ways in which we can select these 3 alike. Now we can select these 3 alike from either 3 e's or 3 n's. So it is simply 2c1. Now we need to select 2 alike. Now out of these 3 e's and 3 n's, one of them is not possible for selection. So from these remaining 2, I have to select any one, and it can again be done in 2c1 ways. So this is simply 4 ways. Now again we have to select 3 alike. So which again is 2c1 and 2 distinct. Now we have to select 2 distinct numbers. Now suppose these 3 alike were 3 e's. Now we have N, D, I, P, and T. That is 5 distinct letters from which we can select these 2 distinct letters, and it can be done in 5c 2 ways. Now 2c1 is 2 and 5c2 is 10. So this value is simply 20. Now we have to select 2 alike and 2 alike. Now 2 alike can be either 2 e's or 2 n's or 2 d's. So from these 3 we have to select any 2. Now it can be done in 3c 2 ways. And then we have to select 1 distinct. Now 2 of them, they are already selected. So from these remaining 4 distinct letters, we have to select any one, and it can be done in 4c 1 ways, and it will be simply 12. Now we have to select 2 alike. So from these 3, we have to select any one. So it is 3c1. And now from the remaining 5 letters, we have to select any 3. So it will be 5c3, and it will be, now this is 3 and 5c3 is 10. So it will be simply 30. And then 5 distinct. So we have 6 distinct letters. From these 6, we can select any 5 in 6c5 ways, which is simply 6. So total number of ways is simply sum of all these. So this is 24, 24 plus 12, 36, 36 plus 6, 42, 42 plus 30, 72. So total number of ways of selecting 5 letters from this word is 72. So value of x is 72, and we need to find sum of digits of x. Now sum of digits is simply 7 plus 2, that is 9. So answer to this question is 9. Now here the question is, which of the following statements is or are true? Now the first question is, in a 12-storied house, 10 people enter the lift cabin at a ground floor. It is known that they will leave lift in groups of particular 2, 3 and 5 people at different story. The number of ways this can be done if the lift doesn't stop at first and second floor is 720. Now clearly it is given that group of particular 2, 3 and 5 people. So we need not distribute these people. We just have to select 3 different floors from 12 floors, but it is given that this lift, it doesn't stop at first and second floor. So that means from remaining 10 floors, we have to select any 3 floors, and it can be done in 10c 3 ways. And then at these 3 floors, these 3 groups, they can be arranged in factorial 3 ways. So this is nothing but this is 10p3, 10 into 9 into 8, which is 720. That means this option A, it is correct. Now we'll come to the second one. It says each of 3 ladies have brought their one child for admission to a school. Principal wants to interview the 6 persons one by one, subject to the condition that no mother is interviewed before her child. The number of ways in which this interview can be arranged is 90. Now total number of ways of arranging these 6 people is simply factorial 6. Now it says the condition is no mother is interviewed before her child. So for this first pair of mother and child must come before mother. So that means it has to be divided by factorial 2. Again for the second one, it should be same. And for the third one, it should also be same. So this value will be factorial 6, which is 720 divided by 8. And that is 90. That means this option B is also correct. Now the C is number of ways in which one can put 3 balls numbered 1, 2 and 3 in 3 boxes labeled A, B and C such that at most one box is empty is equal to 18. Now since balls are numbered and boxes are labeled, that means there are distinct balls and distinct boxes. Now for this ball number 1, we have 3 choices. It can be put into any box A, B and C. So for this first we have 3 choices. For this second also we have 3 choices. And for this third also we have 3 choices. So if we do not have any restriction, then total number of ways of distributing 3 distinct balls in 3 distinct boxes is 27. Now it says at most one box is empty. So we have to subtract all those cases in which either any 2 boxes are empty or all the 3 boxes are empty. Now all the 3 boxes, they cannot be empty. So we have to subtract all those cases where 2 boxes are empty. Now we can select these 2 boxes in 3C2 ways. Now since we are left with 3 balls and 1 box, so these 3 balls, they can be distributed into 1 box in simply one way. So it will be simply 27 minus 3 and it is 24. So that means this C, it is incorrect. Now if we look at this option D, it says a box contains 5 different red balls and 6 different white balls. The total number of ways in which 4 balls can be selected, taking at least 1 ball of each color is 310. So we have to select 4 balls. It can be 1 red, 3 white, or 2 red, 2 white, or 3 red and 1 white. Now 1 red, it can be selected in 5C1 ways. 3 white is 6C3 plus 5C2 into 6C2 plus 5C3 into 6C1. Now this is 5. Now 6C3 is 20 plus 5C2 is 10. 6C2 is 15. 5C3 is 10 and 6C1 is 6. So it will be 100 plus 150 plus 60 and there is nothing but 310. So that means this option D, it is correct. So the correct options are A, B and D. Now here the question is, a fair coin is tossed n times. Let an denotes the number of cases in which no 2 heads occur consecutively. Then which of the following is or are correct? Now A1. So that means we have tossed the coin 1 times. So number of cases in which no 2 heads occur consecutively is simply 2. So that means value of A1 is 2. So option A, it is correct. Now what about A2? Now in A2, for this first case, we have 2 choices. For the second case also, we have 2 choices. That means total number of choices that we have is simply 4. And from these 4, we'll remove the case where 2 heads occur consecutively. So it is simply 3. So value of A2 is 3. So that means option B is also correct. Now suppose we toss this coin n times. And it is given by AN. Now on this nth toss, it could be either tails here or it could be heads here. Now if it is tails here, then here it can be either tails or heads. So it is nothing but it is A n minus 1 and plus if we have got heads here, we know that it will be definitely tails here. Here it could be either tails or heads. So this is nothing but this is a n minus 2. So we get this recurring relation that a n it is equal to a n minus 1 plus a n minus 2. Now with these a1 and a2 we can generate the sequence. So first one is 2, then 3, then 2 plus 3 5, 5 plus 3 8, 8 plus 5 13, 13 and 8 21, 21 and 13 34, 34 and 21 it is 55. So first one is 2, second one is 3, fifth one is 13. So A5 it is 13 and not 14, and 6, 7 and 8, A8 is 55. So the correct options are A, B and D. Now here the question is 4 balls numbered 1, 2, 3, 4. So we have 4 balls and they are distinct. They are numbered 1, 2, 3 and 4, and they are to be placed in 5 boxes which are numbered 1, 2, 3, 4 and 5. Now we have to arrange them in such a way that exactly one box remains empty and no ball goes to its own numbered box. Now we have to find number of ways this can be done. Now we'll take up 2 separate cases. Case 1, when we have these 4 balls and these 4 boxes. Now we have to arrange these 4 balls into these 4 boxes so that no ball goes to its own numbered box, and it is nothing but it is derangement 4. So it will be simply D4, and that's our first case. So in this first case, all these 4 balls 1, 2, 3, 4 they go into these 4 boxes 1, 2, 3 and 4. Now we'll consider the second case when any one ball out of 1, 2, 3, 4 it goes to 5. So what we'll do is we'll assume an imaginary ball 5, and then we'll consider derangement of these 5 objects, and it can be done in simply D5 ways. So wherever this 5th ball goes, that box will be empty, and or these 4 anyone can go to this box number 5. So the total number of ways is given by D4 plus D5. Now D4 is nothing but factorial 4 into this summation minus 1 to the power r upon factorial r, where r varies from 0 to 4 plus, and D5 is factorial 5, this summation r varies from 0 to 5 minus 1 to the power r upon factorial r, which is your option C. Now D4 is nothing but D4 is 9, and we know that D5 is 44. So this value will be 9 plus 44, which is 53. So the only correct option is this option C. Now here the question is, let Fn denote the number of ways in which n letters go into n envelopes so that no letter is in correct envelope. Where n is greater than 5, then Fn minus nFn minus 1 equals what? Now this is nothing but this is recursive relation in derangements, which we have already studied. So suppose we have these n letters which are given by L1, L2, L3 and Ln, and then we have n envelopes which are given by E1, E2 and En. Fn is total number of ways in which we can distribute these letters into envelopes so that no letter is in correct envelope. Now for that, what we'll do is we'll assume that in this E1 there is one of the letter from these n minus 1 letters. So any one letter for E1 it can be selected in n minus 1 C1 ways. So this is n minus 1 C1. Now suppose the selected letter is LK. Now we have 2 cases. Case 1, when this LK goes into E1 and L1 goes into EK, then we are left with derangement of remaining n minus 2 letters. So it will be nothing but F n minus 2. Or this other case where LK goes to E1 but L1 it doesn't go to EK. Now in this case we'll have derangement of remaining n minus 1 letters. So it will be simply f n minus 1. So from here we will get this recursive relation that f n equals n minus 1 f n minus 2 plus f n minus 1. Now we can write this as f n, and this is n minus 1 f n minus 2 plus n f n minus 1 minus f n minus 1. Now we will take it on the left hand side. We can write f n minus n f n minus 1. It will be n minus 1 f n minus 2 minus f n minus 1, and that's your option B. Now this question is actually nothing but proof of recursive relation in derangement, which is dn. It is given by n minus 1 into dn minus 2 plus dn minus 1. Now here the question is, the letter of word arrange are arranged in all possible ways. Let n be number of arrangements in which two A's are together and two R's are not together, and n is number of arrangements in which neither the two A's nor the two R's are together. Then we need to find the value of m and n. Now in this word arrange, we have two A's, two R's, and then we have n, g, and e. Now for this m, it says two A's are together. So if two A's are together, we'll use string method. So we'll combine them, and then two R's are not together. So we have to use gap method also. So we have used string for these two A's, and then first we'll arrange these 2A, n, g, and e, which can be done in factorial 4 ways. And once we have arranged these 4 objects, we have created 5 gaps, and we have to place these two R's in these 5 gaps. So it can be done in 5C 2 ways. So value of m will be simply factorial 4, which is 24, and 5C2 is 10. So value of m is 240. Now for this n, it says neither two R's are together and nor two A's are together. So what we'll do is we'll find total number of arrangements, and total number of arrangements is given by factorial 7, factorial 2, and from that we'll subtract all the cases where at least one of A or R they are together. Now if two A's are together, now we have 6 objects. It can be done factorial 6 divided by factorial 2 plus now 2 R's are together, which again is factorial 6 upon factorial 2 minus A intersection B, which is when both 2 A's and 2 R's are together. This is nothing but this is factorial 5. Now factorial 7 upon factorial 2, it is 7 into 720 by 4 minus now factorial 6 upon factorial 2 plus factorial 6 upon factorial 2, it is 720, and then plus factorial 5, which is 120. Now this is 720 common, then 7 minus 4 upon 4. So this is 3 by 4. So it will be 3 by 4 into 720 plus 120. So this is 540 plus 120. So it will be 660. So value of n is 660. So now we have m and we also have n. We can find the value of m plus n. So value of m plus n will be 240 plus 660. So it will be 00, and that is 900. That means option A is correct. And if we find n minus m, it will be 660 minus 240. So this is 0, 2 and 4. That is 420, and that's your option D. So the correct options are A and D. Now here the question is, 13 persons are sitting in a row. The number of ways in which 4 persons can be selected so that no 2 of them are consecutive is equal to which of the following. Now this is non-consecutive selection in a row, and we have already studied it one of the previous videos, and which is if we have n objects arranged in a row, and we have to select r objects so that no two objects are consecutive. It is given by n minus r plus 1 cr. Now in this case, value of n is 13 and we have to select 4. So total number of ways of selecting 4 persons so that no two of them are consecutive is given by 13 minus 4 plus 1 c4, which is 10 c4. Now 10 c4 is 10, 9, 8, 7, 4, 3, 2, 1. So this is 8, this is 3. So it will be simply 210. So this value, it is 210. Now we have to look at all the 4 options. Now the first one is number of ways in which all the letters of the word marriage can be permuted if no two vowels are together. Now here the vowels are A, I and E, and consonants are M, R, G. Now we have to separate these vowels. We'll use gap method. So first we'll arrange M, R, G, and it can be done in factorial 4 divided by factorial 2 ways. Now since no two vowels are together, we have to arrange these vowels in gaps, and we have 5 gaps. So out of these 5, we have to select any 4. It can be done in 5C4 ways, and these 4 gaps, these 4 letters, they can be arranged in factorial 4 divided by factorial 2 ways. Now factorial 4 divided by factorial 2 is 12. So 12 into 12 will be 144 into 5, and that is 720. So number of ways in which this can be done is 720, and it is not equal to 210. So this option A, it is incorrect. Now the second one is number of numbers lying between 100 and 1000 using only the digits 1, 2, 3, 4, 5, 6, 7 without repetition. So we have a 3-digit number. Now for this first place, we have 7 choices. For this second place, we have 6 choices. And for this third place, we have 5 choices. So it will be 30 into 7, which is 210. That means this number is same as 210. Now this third part is number of ways in which 4 alike chocolates can be distributed among 10 children so that each child get at most 1 chocolate. Now since the chocolates are alike, for any child, total possibilities are represented by x to the power 0 plus x to the power 1. So for one child, this is 1 plus x. For the next one, it will also be 1 plus x, and it will be 1 plus x for all the 10 children. So total possibilities, they can be expressed as 1 plus x to the power 10. Now we have to distribute 4 chocolates. So that means from this we have to find coefficient of x to the power 4. Now we know that coefficient of x to the power r in 1 plus x to the power n is simply ncr. So this coefficient is given by 10c4, which is 210. So that means this option C is also correct. And then finally we have this D, which is number of triangles that can be formed by joining 12 points in a plane, of which exactly 5 are collinear. Now what we'll do is, if we consider these 12 points such that no 3 of which are collinear, then number of triangles that can be formed is 12c3. Now from this we'll subtract all those cases where a triangle will not be formed. So if we select any 3 points from these collinear points, we won't get a triangle. So total number of triangles that can be formed is given by 12c3 minus 5c3. Now 12c3 is 12, 11, 10, and this is 6, and minus 5c3 is 10. So this is 6. So this is 220 minus 10, and it will be 210. So that means this option D is also correct. So the correct options are B, C, and D. Now here the question is the number of ways in which we can choose 2 distinct integers from 1 to 200 so that difference between them is at most 20 is given by which of the following. Now if one of the number is 1, then the condition that difference between the 2 numbers is at most 20, we can select the other number as either 2, 3 up to 21. So we have 20 choices. Now, if we select this first number as 2, then also we'll have these choices from 3 to 22. In the same way, for 3 also, we'll have choices from 4 to 23. So each time we'll get 20 choices for these numbers, and it'll continue till the case when this first number is 180. If the first number is 180, then the other number could be 181, 182 up to 200. So it'll be again 20 cases. So if the first number is from 1 to 180, each time we'll have 20 ways to select this second number. Now, if the first number is 181, then this other number, it can be chosen from 182 to 200, which now is 19 cases. Now for 182, it'll be from 183 to 200, which is 18 cases. And finally, if we choose 199, then the only possibility is 200, which is 1 case. So total number of cases will be 20 plus 20 plus 20, 180 times. So it will be 20 into 180 plus the series, which is 19 plus 18 plus 17 up to 3, 2 and 1. Now this is 3600, and this is sum of first 19 natural numbers, which is n plus 1 by 2, which is 190. So this value will be 3790, and that's your option A. Now if we look at this option B, which is 200 C2 minus 180 C2, 200 C2 is 200 into 199 by 2. So it will be 19900 minus, and 180 C2 is 180 into 179 by 2, which is 90 minus 179 into 90. And this value is also 3790. That means option B is also correct. Now option C is 180 into 20 will be 3600 plus 190, which again is 3790. And option D is 180 C2, so it will be 180 179 divided by 2. Now 179 into 90 is 16110. That means this option D is incorrect. So the correct options are A, B and C. Now here the question is the number of ways in which 5 different books to be distributed among 3 persons so that each person gets at least 1 book is equal to number of which of the following. Now here we have 5 distinct books and it has to be distributed among 3 persons so that each person gets at least 1 book. Now there are many ways to do it. One of the ways using condition of onto functions. So we have 5 books which are B1, B2, B3, B4 and B5, and they are to be distributed among 3 persons which are say P1, P2 and P3 so that each person gets at least 1 book. That means if we define function from books to people, then it should be an onto function. And in one of the previous videos, we have already studied that number of onto functions is given by total number of functions. Now for each book, we have 3 choices. So it will be 3 to the power 5 minus all those cases where at least 1 is empty. Now from these 3, we can select any one. It can be done in 3C1 ways. So for these books, we have 2 options now. So it will be 2 to the power 5 minus, now 2 are empty. So this can be done in 3C 2 ways. Now all the books, they'll go to this remaining person. So it is given by 3 to the power 5 minus 3 into 2 to the power 5 plus 3. Now 3 to the power 5 is 243 minus 32 into 3, 96 plus 3, and which is 150. So there are 150 ways in which we can distribute these 5 different books among 3 people so that each person get at least 1 book. Another method is using balls and boxes problem. So we have 3 boxes, say P1, P2 and P3, and we have to distribute 5 distinct balls which are B1, B2, B3, B4 and B5. Now since another box is empty, it can be done in 2 ways. Either it is 3, 1, 1 or 2, 2, 1. Now first we'll distribute the books, and it can be done factorial 5 divided by factorial 3, and then these two are identical, divided by factorial 2, and then these 3 groups, they can be distributed in 3 boxes in factorial 3 ways. So it will be simply factorial 5 divided by factorial 2, and that is 60. Now for 2, 2 and 1, it will be factorial 5, factorial 2, factorial 2, and since these two are identical, it will be factorial 2, and then again these 3 groups, they can be distributed in factorial 3 ways. Now this is 120 into 6 divided by 4 into 2. So this is 3, this is 30, so it will be 90. Now 60 plus 90 is again 150. So the total number of ways in which we can distribute 5 different books among 3 persons so that each person gets at least 1 book is 150. Now we look at all these 4 options. Now this first option is 5 persons are allotted 3 different residential flats so that each person is allotted at most 1 flat and no 2 persons are allotted the same flat. So here we have 5 persons, P1, P2, P3, P4 and P5, and we have 3 flats, F1, F2 and F3. Now each person is allotted at most 1 flat and no 2 persons are allotted the same flat. So these 3 flats, they'll be allocated to any of these 3 people. So out of these 5, we have to select any 3, which can be done in 5C3 ways. Now these 3 people and these 3 flats, they can be arranged in factorial 3 ways. So it'll be 5C3, which is 10, and factorial 3 is 6. So it'll be 60 ways, which is not equal to 150. So this option A is incorrect. Now the second one is number of parallelograms formed by one set of 6 parallel lines and other set of 5 parallel lines that goes in other direction. Now for parallel lines, we need to select 2 parallel lines from one set and 2 parallel lines from another set. Now from this first set, 2 lines can be selected in 6C2 ways, and from the second set, 2 lines can be selected in 5C2 ways. Now 6C2 is 15 and 5C2 is 10, so this value is 150. That means this option B, it is correct. Now if we look at this third, it is 5 different toys are to be distributed among 3 children so that each child gets at least 1 toy. So this is same as this first situation, 5 different books distributed among 3 persons so that each gets at least 1 book. So here instead of books, we have toys, and 3 persons become 3 children and each child gets at least 1 toy. So it has to be again 150. So this option C is again correct. And now the last one is 3 professors of mathematics are assigned 5 different lectures to be delivered so that each professor gets at least 1 lecture. So now we have 5 different lectures, L1, L2, L3, L4 and L5, and we have 3 professors, P1, P2 and P3. So each lecture, it must have a professor, and each professor also, it must have at least 1 lecture, which again is condition of onto functions, which again will be 150. So this option D is also correct. So the correct options are B, C and D. Now here the question is, if x1 plus x2 plus x3 up to xr is n, then number of non-negative integral solutions is given by n plus r minus 1 cn, and number of positive solutions is given by n minus 1 c r minus 1. Now the first question is, if a, b, c, b, 3 natural numbers in AP, then number of solutions of a plus b plus c equals 21 is. Now since a, b, c are in AP, that means 2b equals a plus c. Value of b will be simply 7. So this b, it is fixed. So here we'll have this condition that value of A plus C, it must be 14, where A and C are natural numbers. So the possibilities are, if A is 1, C is 13, 2 and 12, and we'll go all the way up to 13 and 1. So there are 13 such cases. So there are 13 ways in which we can select these three natural numbers in AP, so that A plus B plus C is 21. So the correct option is this option C. Now the next one is number of ways of distributing 22 identical toys among 4 children when each child must get an odd number of toys is equal to which of the following. Now suppose first child gets 2 n1 plus 1 toys, second child gets 2 n2 plus 1 toys, third child 2 n3 plus 1, and fourth child 2 n4 plus 1, where any ni is non-negative integer. Now sum of all the toys will be 2 n1 plus n2 plus n3 plus n4 plus 4, and it is equal to 22. So 2 n1 plus n2 plus n3 plus n4 will be 18. We'll get this equation as n1 plus n2 plus n3 plus n4 equals 9, and we need to find number of non-negative integral solutions. Number of non-negative integral solution is given by n plus r minus 1 c r minus 1, so which is 12c3. So the correct option is 12c3, which is same as 12c9. That's your option B. So total number of ordered pairs of P and Q will be 5 into 9 into 5, and it is 225. That's your option C. Now here the question is, let Sn be set of all n-digit numbers. The numbers of numbers in S6 consisting of digits 0, 3 and 5 only, with each of them appearing at least once is. Now we'll solve this question using inclusion exclusion. So first we'll find total number of 6-digit numbers that can be formed using these 3 digits. So it is a 6-digit number. Now for this first place we have 2 choices. It can be either 3 or 5. So we have 2 choices here, and for these remaining 5 places it will be 3 choices each. So we can write this as 2 into 3 to the power 5, which is 486. Now from these total numbers we'll remove all the cases where at least one of these 3 digits is missing. So first we'll find all the cases in which at least one is missing. Now this missing digit, it could be 0 or 3 or 5. Now if the missing digit is 0, then total number of numbers that can be formed is simply 2 to the power 6. Now if the missing number is 3, for the first place we have only one option, and for remaining 5 we have 2 options each. In the same way for 5 also it will be 2 to the power 5. So this is 2 to the power 7, and that is 128. Now from this we'll subtract all those cases where 2 of them are missing, because we know that n A union B union C is NA plus NB plus NC minus N A intersection B, B intersection C, and C intersection A. Now if 1 and 3 they are missing, it will be this one case, all the numbers formed with 5, minus if 0 and 5 are missing, again one case, and if 3 and 5 are missing, and if both 3 and 5 are missing, it will be simply 0. So there will be no other case. So it will be 126. So there are 126 cases in which at least one of 0, 3 and 5 they are missing. So total number of cases or total number of numbers in which all these digits they appear at least once, it is given by 486 minus 126, which is 0, 6 and 3. So it will be 360, and that's your option A. Now the next question is the number of numbers in S6 having exactly 3 different digits. Now these 3 different digits, they may have 0. So it could be 0 and then any 2 digits A and B, or it can be all 3 non-zero digits A, B and C. Now if one of the digit is 0, then We have to select these two digits and it can be done in 9C two ways. Now once we have 0, A and B, this case it is similar to this first case when we have 0, 3 and 5. In this case, total number of numbers which have each digit at least once, it is 360. So it will be 9C2 into 360 plus, now all these three numbers, they are non-zero. So it will be 9C3, and from these three numbers, total number of numbers that can be formed which have all the digits at least once, it will be given by this inclusion exclusion. For each place we have three options, so it will be 3 to the power 6 minus at least one is missing, so it is 3C1 to the power 6 minus 2 are missing, 3C2 1 to the power 6. So this value will be 36 into 360 plus 9C3. 9C3 is 987 and this is 3 into 2. So this is 3, 4, 12. 12 into 7 is 84. Now 3 to the power 6 is 7 to 9 minus this is 3 into 2 to the power 6, which is 64 and plus 3. And this value, it is equal to 58320, and that's your option B. Now here the question is, if n is the number of 8-digit numbers formed using all the digits 1, 3, 4, 5, 6, 7, 8, 9, which are divisible by 275. Now 275 is 5 square into 11. So this number, it must be divisible by 25 and it must also be divisible by 11. Now we know that divisibility by 25 is when the last two digits are either two zeros or they are divisible by 25. So last two digits, they can only be 75. So we have this 8-digit number in which last two digits, it must be 75. So these two places, they are fixed. Now we have to distribute these remaining numbers 1, 3, 4, 6, 8 and 9 so that this number is also divisible by 11. Now suppose this is A, B, C, D, E and F. Now it is divisible by 11 when sum of digits at odd places, which is A plus C plus E plus 7 minus sum of digits at even places, which is B plus D plus F plus 5, it must be a multiple of 11. So we can write A plus C plus E minus B plus D plus E, it must be equal to 11k minus 2. Now if we look at the remaining digits are 1, 3 and 9, which are odd, and 4, 6 and 8, which are even. Now whichever way we distribute them, one of this combination A plus C plus E and B plus D plus E will be even and the other combination will be odd. So this number will be an odd number. So this k, it cannot be an even number. So this k, it cannot be 0. So the only other option that we have here is value of k must be 1. So we'll have this condition that A plus C plus E minus B plus D plus E, it must be equal to 9. Now if we look at these digits, then we can figure out this A, C and E, it must be 3, 8 and 9, whose sum is 20, and B, D and E, it must be 1, 4 and 6, which is 11, and 20 minus 11 is 9. So we have to distribute these three digits 3, 8 and 9 in these three positions, and it can be done in factorial 3 ways, and we have to distribute 1, 4 and 6 in these three even positions, which again is factorial 3. So it will be 6 into 6, 36. So number of 8-digit numbers which are divisible by 275, it is 36. Now under root of n, it is 6. So under root of n belongs to z. Option A is correct. N can be expressed as sum of twin primes, and twin primes is pair of consecutive prime numbers. So we can write this as 19 plus 17, and they are consecutive primes. So that means this option B is also correct. Under root n doesn't belong to z. Option C is incorrect. And D is n can be expressed as sum of cubes of 3 consecutive positive integers. So we can write this as 1 plus 8 plus 27, which is 1 cube plus 2 cube plus 3 cube, and that's your option D. So the correct options are A, B and D. Now here the question is, let omega be a cube root of unity and S be set of all non-singular matrices of the form 1AB, omega 1C and omega square, omega and 1, where each of A, B, C is either omega or omega square. If number of distinct matrices in set S is n, then which of the following options are correct? Now matrix is a non-singular matrix. Non-singular is determinant is unequal to 0. Now we find determinant of this matrix, and which is, say, determinant of A, it will be 1 into 1 minus C omega minus A into omega minus C omega square, and then plus B and LB omega square minus omega square, which is 0. So this determinant of A will be 1 minus C omega minus A omega plus AC omega square. Now we can write this as 1 minus C omega, and here we'll take A omega common, so it will be 1 minus C omega. So determinant of A will be 1 minus A omega into 1 minus C omega, and it must not be equal to 0. That means this A, it must not be equal to 1 upon omega, which is omega square, and C also must not be equal to omega square. So for these A and C, we only have one choices each. So this A, it can only be omega, and this C, it can also be omega. Now this result, this determinant, it doesn't depend on B. So this B, it can have two choices. So it can be either omega or omega square. So value of n is simply 2. So option A is correct, and option C is correct, and option D is also correct. So the correct options are A, C and D. Now here the question is, let A to A be an invertible function where A equals 1, 2, 3, 4, 5, 6, the number of these functions in which at least 3 have self-image. So we have this function defined from A to A. This is A and this is also A. So this is 1, 2, 3, 4, 5, 6, and this is also 1, 2, 3, 4, 5 and 6. Now we need to find number of invertible functions, that is number of 1, 1 and onto functions in which at least 3 have self-images. Now we'll consider the cases where at least 3 or more have self-image. Now this is when exactly 3 have self-image, when exactly 4 have self-image, when exactly 5 has self-image, and when exactly 6 have self-image. Now if 3 elements have self-image, we have to select which 3, and it can be done in 6C 3 ways. Now we have selected these 3 elements and they have self-image. Now remaining 3, they must not be mapped to itself. So that means we have to consider derangement of 3. So it will be 6C3 into D3. Plus, now 4 have self-image, so it will be 6C4 and then derangement of 2. Now if 5 have self-image, then 6 also will have self-image. So this case is not possible. And all the 6 they have self-image, this case is only 1. Now 6C3 is 20 and D3 is 2. 6C4 is 15 and D2 is 1 and then plus 1. So it will be 40 plus 15 plus 1, which is 56, and that's your option 2. Now here the question is, the number of functions from set A, which is 0, 1, 2, and B, which is 0, 1, 2, 3, 4, 5, 6 and 7 such that Fi is less than equal to Fj when I is less than j. Now this is non-increasing function. Now this we have studied in one of the previous videos. Now we know that if in set A we have n elements and in set B we have m elements, then number of non-increasing or non-decreasing functions, it is given by n plus m minus 1 c n ways. So in this case, value of n is 3 and value of m is 8. So it will be 3 plus 8 minus 1 c 3 ways, which is 10 c3, which is your option number 3. Now here the question is, the set S contains first n natural numbers, and if X denotes set of all subsets of S containing exactly 2 elements, then we have to find the value of summation A belongs to X minimum A, and it is n plus 1 C lambda. We have to find the value of lambda. Now first we will find how many sets are there in which minimum element is 1. Now since each subset contains 2 elements, we already have 1 element. We have to select this other element from remaining n minus 1 elements, and it can be done in n minus 1 C1 ways. So which is n minus 1. So there will be these n minus 1 subsets in which minimum element is 1. Now if the minimum element is 2, then this other element, it can be selected from remaining n minus 2 elements, which is n minus 2 C1, and there will be n minus 2. Now for 3, it will be n minus 3 C1, which is n minus 3. And finally, if minimum is n minus 1, then we'll have 1 C1. That is only one choice. So sum of all the minimum values in these subsets will be this 1 into n minus 1, 2 into n minus 2 up to n minus 1 into 1, which is nothing but this summation r into n minus r, where the value of r varies from 1 to n minus 1, or we can also take n because n minus n is 0. So from 1 to n. So it will be n into this summation r minus summation r square. Now this is n into n plus 1 by 2, and this is n plus 1 2n plus 1 divided by 6. Now here we'll take n plus 1 by 2 common. So now we'll have n minus 2n plus 1 by 3, which is n plus 1 n minus 1 by 6. That is n into n square minus 1 by 6. Now this is nothing but this is n plus 1 C3, because it will be n plus 1 n minus 1 by 6. So here the value of lambda, it must be equal to 3, and that is the answer to this question. Now here the question is, consider n cross n graph paper where n is a natural number. Consider the right angle isosceles triangles whose vertices are integer points of this graph, whose sides forming right angle are parallel to x and y axis. If number of such triangles is 2 upon k, n plus 1, 2n plus 1, then we need to find the value of k. So we have this n cross n graph. Now what we'll do is, in this n cross n graph, we'll find total number of squares that can be formed in this grid. Now starting with the smallest square, whose length is 1 by 1. So here we have n such units, and here also we have n such units. So number of such squares, it will be simply n square. Now we consider square of 2 unit length. Now for 2 unit length, we have to select 2 consecutive lengths horizontally, 2 consecutive lengths vertically. Now this we have already studied in consecutive selection. Now from these n, 2 consecutive, it can be selected in n minus 2 plus 1 ways. So it will be n minus 2 plus 1 for horizontal and n minus 2 plus 1 for vertical. It will be n minus 1 square. Now for 3, it will be simply n minus 2 square. And finally, this largest square of side n. So it will be simply 1 square. So number of squares in this grid, it is given by 1 square, 2 square up to n square, and which is n plus 1, 2n plus 1 whole divided by 6. Now we know that in any square, we can have 4 right angle triangles. So this is 1, this is 2, and then this is your third, and that's your fourth. So in any square, we'll have 4 possible right angle triangles. So total number of right angle triangles will be simply 4 into number of squares, which is n plus 1, 2n plus 1 whole divided by 6. Now we can write this as 2n plus 1, 2n plus 1 whole divided by 3. Now here the value of k is simply 3. So answer to this question is value of k is 3. Now here the question is, consider the following statements. The first one is the number of a cube that can be painted with 6 different colors is equal to 30. So we have this cube. Now since there is symmetry in this problem, we can paint first face with any color, and then all the colors, they'll be arranged relative to this first color. So this first color, it could be any color, and suppose this is blue. Now for this opposite face, we'll have 5 choices. So now we have 2 colors, one on the top and one at the bottom. Now for these remaining 4 faces, we have to arrange these 4 colors in a circle, and it can be done in factorial 3 ways. So total number of ways in which we can paint this cube is 5 into factorial 3, which is 5 into 6, 30. That means this statement 1, it is true. And we have discussed this problem at length in one of the previous videos. So you can refer to that video if you have any doubt in the concept. Now the second question is, each of the 3 ladies have brought 1 child for admission to a school, and principal wants to interview 6 persons one by one, subject to the condition that no mother is interviewed before her child. Now total number of arrangements is factorial 6. Now this first mother, it should not be interviewed before the child. So it should be divided by factorial 2. Again for the second mother, it will be factorial 2. And for third mother also, it will be factorial 2. So that is 720 divided by 8, and it will be simply 90. That means this option 2 is also correct. Now this third one is number of ways in which one can put 3 balls numbered 1, 2, 3 in 3 labeled boxes A, B and C such that at most 1 box is empty. Now we have 3 distinct balls, 1, 2 and 3, and 3 distinct boxes A, B and C. Now total number of ways in which we can distribute these 3 balls in these 3 boxes is 3 to the power 3, which is 27. Now from this, we'll subtract all the cases in which 2 or more boxes are empty. Now all these 3 boxes, they cannot be empty. So we'll have to subtract all the cases where either A and B are empty, or B and C are empty, or A and C are empty. So it is 3C2. Now if A and B are empty, then all the 3 balls, they'll go to C. So there is only one way. So total number of ways is 27 minus 3, and it is 24. That means this third option, it is incorrect. And the fourth one is, a box contains 5 different red balls, 6 different white balls. The total number of ways in which 4 balls can be selected, taking at least 1 ball of each color, is 310. Now this question also we have solved previously in one of the questions. So that means this option 4 is also correct. So statement 1 and 2, they are correct. So option A is correct. 2 and 4 are correct. Option B is also correct. 1 and 3 are correct. No. All the statements are correct? No. So the correct options are A and B. Question is, on a chess board as shown, P1 and P2 are 2 persons which start moving towards each other. Each person moving with same constant speed. P1 can move only to the left or downwards along the lines, while P2 can move only to the right or upward along the lines of chessboard. Now this should be P2 and this should be P1. Now it says total number of ways the two person meet at some point is K. So we have to find total number of ways in which they'll meet. They'll meet if they'll cover the same distance, because they both move with same constant speed. So they can only meet along this diagonal. So either they can meet at this point or this point or this point. So they can meet at the points which lie along the diagonal of this grid. Now if they are going to meet at this point, then this P2, it must move in this direction, and P1, it must move in this direction. So there is only one possible way. So this is only possible in one and one way. Now for the second point, this P2, it must travel one horizontal distance and 7 vertical distances. So one horizontal and 7 vertical, they can be arranged in factorial 8 upon factorial 7 factorial 1 ways. And the same way for the second one also, we have to select 7 horizontal and 1 vertical, which again is factorial 8 upon factorial 7 factorial 1. So it will be this square. So we can write this first one as 8c8 square. This second one as 8c7 square. Now for this third point, it will be 2 horizontal and 6 vertical, which is factorial 8 factorial 6 factorial 2, and again it will be square of that. So it will be 8c6 square, and finally for this point it will be 8c0 into 8c0. So this number k, it will be 8c0 square plus 8c1 square up to 8c8 square, which is 2ncn, and n in this case is 8, so it will be 16c8, and this value is 12870. Now we need to find sum of digits of k. Now sum of digits of k will be 1 plus 2 plus 8 plus 7 plus 0. So this is 10, 17 and 18. So this is 18, and that's your option A, and the middle digit is 8, and that's your option C. So the correct options are A and C. Now here the question is, let A, B, C, D and E be smallest positive integers having 10, 12, 15, 16 and 20 positive integral divisors, then which of the following options is or are correct? Now we know that for any number n, if we express them as powers of prime, P1 to the power A1, P2 to the power A2, P3 to the power A3, then number of divisors is given by A1 plus 1 into A2 plus 1 into A3 plus 1 and so on. And since the number is smallest, we can write this number as sum 2 to the power A, 3 to the power B, 5 to the power C, 7 to the power D and so on. Now in this case, number of divisors will be A plus 1, B plus 1, C plus 1, D plus 1 and so on. Now here we want number of divisors to be 10. Now we can write this 10 as 5 into 2. So either it will be A plus 1 into B plus 1 equals 5 into 2 or 10 into 1. Now here value of A is 4 and value of B is 1, or value of A is 9 and value of B is 0. So this number A, it can either be 2 to the power 4 into 3 or 2 to the power 9. Now 2 to the power of 4 into 3 is 16 into 3, which is 48, and this number is 512. So smaller of the two number is this 48. So value of A is 48. Now for 12 we can write A plus 1, B plus 1, C plus 1, and it will be either 4 into 3 or 3 into 2 into 2. Now we take them as 4 into 3, then A is 3 and B is 2 In this case, this B will be 2 cube into 3 square, which is 9 into 8, 72. Or the second case where A is 2, B is 1 and C is 1. In this case, B is 2 square, 3 to the power 1 and 5 to the power 1. So this is 15 into 4, 60. So the smaller value is 60. So in this case, value of B is 60. So we'll discard 72. Now for 15, we can write this as 5 into 3. So it'll be simply A plus 1 into B plus 1 equals 5 into 3. So A is 4 and B is 2. So this C will be 2 to the power 4 into 3 square, which is 16 into 9, and that is 144. So value of C is 144. Now for this D, we have this 16. Now for this 16, we have 4 possibilities. Either it can be 2 into 2 into 2 into 2, or it can be 4 into 4, or 4 into 2 into 2, or 8 into 2. Now we solve these 4 cases, we'll realize that minimum we'll get when it is 4 to 2. So value of A is 3, value of B is 1 and value of C is also 1. So this D will be 2 cube into 3 into 5, which is 120. So minimum value of D is 120, and for this E, which is 20, we can write this as either 5 into 4 or 5 into 2 into 2. It will be minimum in this case when the value of A is 4, B is 1 and C is 1. So value of E will be 2 to the power 4 into 3 into 5, which is 240. So value of E must be 240. So these are 5 minimum values. Now value of A plus B, A is 48 and B is 60. So it will be 108. So option A is correct. Now C plus D is 120 plus 144. So it will be 264. So this option B is incorrect. A plus E, 48 plus 240. So it will be 288. Option C is also correct. And A plus E cannot be 300. So the correct options are A and C. Now this is famous 1000 doors problem. And this problem we have already discussed in one of the previous videos. So there I have discussed this problem in detail. Here I'm just going to skim through it. So we have 1000 doors, D1, D2, D3 and D1000. And there are 1000 people, P1, P2, P3 and P1000. Initially all the doors are closed. P1 opens all the doors. P2 closes all the doors which are multiple of 2. P3 changes the status of all the doors which are multiple of 3. And it goes on. So the question is, until lastly P1000 changes the status of D1000, then which of the following options are correct? So we have to find number of doors which are open. Now we know that any door will only be touched by a person whose number is one of the divisors of the door number. Say door number 6 will be touched by P1, P2, P3 and P6. So any door, it can only be touched by a person whose number is a divisor of the door number. Now we need to find how many doors will be open. So a door, it will be open when it is touched by odd number of people. So it will be touched by odd number of people if the number has odd number of divisors. So all the doors which are open will have the number which have odd number of divisors. Now we know that for any number n whose prime factorization is p1 to the power a1, p2 to the power a2 and pk to the power ak, number of divisors is given by a1 plus 1, a2 plus 1 and ak plus 1, and this number, it will be odd when each of a1, a2 and ak, they are even. And if they are even, then all the powers, they are even powers. That means this n, it must be a perfect square. So all the doors whose number is a perfect square of some number, they'll be open, and all other doors, they'll be closed. So such doors are 1 square, 2 square, 3 square and then 30 square is 900, and then 31 square, which is 961. So overall there will be 31 doors which are open. So number of doors which are open is 31, and that's your option A. Now greatest number of consecutive doors that are closed finally. Now this greatest number is between this door number 900 and door number 961, and there are 60 such numbers. So that means this option B is also correct. Option C is the door having greatest number that is finally open is D961. It is also true. And D is greatest number of consecutive doors that are finally closed is 61. No, this is not 61, it is 60. So this option D is incorrect. So the correct options are A, B and C. 5-digit numbers are formed using the digits 0, 1, 2, 3, 4 and 5. Answer the following. How many of them are divisible by 3 if repetition is not allowed? So we have to select 5 digits. Now if we find sum of all these 6 digits, it is n plus 1 by 2, which is 15. Now we have to drop one number such that its sum is still 15. So there will be two such cases. Case 1, when the number is formed with 1, 2, 3, 4 and 5. And then the second case, when we have dropped this 3, so it will be 0, 1, 2, 4 and 5. Now 5-digit numbers that can be formed is factorial 5, and here it will be factorial 5 minus all those numbers that start with 0, which is factorial 4. So total number of such numbers will be 2 into factorial 5 minus factorial 4. Now factorial 5 is 120. 120 into 2 is 240. 240 minus 24 is 216. So this A, it matches with B. Now the second one is how many of them are divisible by 3 if repetition of digits is allowed. Now first we'll find total number of 5-digit numbers that can be formed using these digits. So total number is given by, now for this first place we have 5 options, and then for remaining 4 we have 6 options each. So it will be 5 into 6 into 6 into 6 into 6. Now we know that if first 4 digits are fixed, then in the end we'll have 0, 1, 2, 3, 4 and 5, which are consecutive 6 numbers. Now out of these consecutive 6 numbers, exactly 2 of them will be divisible by. So for every 6 numbers, we'll have 2 numbers which are divisible by 3. So out of these total numbers which are divisible by 3, it will be given by 2 into, now how many groups of 6 numbers we have? So it will be this divided by 6. So it will be 10 into 216, and it will be 2160. So this option, it should be 2160, which is not given in column 2. Now this third one is how many of them are divisible by 3 but not by 2 if repetition is not allowed. So again we have these two cases, numbers formed by 1, 2, 3, 4, 5, and second one, numbers formed by 0, 1, 2, 4 and 5. Now it should not be an even number. So for this 5-digit number, for this last place we have 3 options, and then it will be 4, 3, 2, 1, which is 24 into 3, and that is 72. And here also it should not be an even number. So for this last place we have 2 options. For this first place we have 3 options, and then it will be 3 into 2 into 1. So it will be 9 into 4, which is 36. So it will be 72 plus 36, and that is 108. So this C, it matches with Q. And finally, number of 4-digit numbers which are divisible by 5. Now here it is a 4-digit number. So we have 4 places. It is divisible by 5 if the last digit is either 0 or if it is 5. Now if it is 0, then for this first place we have 5 options. For second one we'll have 4, and for third one we'll have 3 options. So it'll be 60 ways, and if it is 5, then we have 4 into 4 into 3. 12 into 4, 48, which again is 108. So this D, it also matches with Q. So A matches with B, B doesn't match with anyone, C and D, they both match with Q. Now here the question is, let NP represents the number of points P alpha beta lying on rectangular hyperbola xy equals factorial 15 under the conditions given in column 1, and we have to match entries in column 1 with column 2. Now first we'll express this factorial 15 as exponent of primes. So exponent of 2 in factorial 15 will be 15 by 2 plus 15 by 2 square 15 by 2 cube. Now this is 7 plus 3 and plus 1, so it is 11. Exponent of 3 in 15, it will 15 by 3, 15 by 9, which is 5 plus 1, 6. Exponent of 5 in factorial 15, it will be 15 by 5, 3. Exponent of 7 in 15, it will be 15 by 7, 2. Exponent of 11, 15 by 11, which is 1. And exponent of 13 in 15, it will be 15 by 13, which is also 1. So we can write this xy as 2 to the power 11 into 3 to the power 6 into 5 cube into 7 square into 11 into 13. So this is how we can express this factorial 15. Now the first one is number of points such that alpha and beta, they both are integers. Now for this, we'll find number of ways in which we can factorize factorial 15 in two parts. So here will be 11 plus 1, 6 plus 1, 3 plus 1, 2 plus 1 into 2 into 2. So it will be 12 into 7 into 4 into 3 into 2 into 2, which is 4032. If we consider positive integers x and y, there will be 4032 factors. And then since alpha and beta, they can be positive as well as negative integers. So total number of ways in which we can find this alpha beta or this NP, it will be simply 2 into 4032, and there will be 8064. So this A, it matches with T, 8064. Now the second one, alpha beta are positive integers and HCF of alpha beta is 1. So we have to factorize this number in co-prime factors. Now number of co-prime factors, it is given by 2 to the power of p minus 1, where p is number of distinct primes. Now here we have 6 distinct primes. So number of ways in which we can factorize this number in two co-prime factors is 2 to the power 5, which is 32, and then we can interchange x and y. So total number of such numbers. So in this case, NP, it will be simply 2 into 32, which is 64. So this B, it matches with Q. Now for this third case, when alpha beta belongs to positive integers and alpha divides beta. For this, what we'll do is, suppose in x, we have 2 to the power a, and in y, we have 2 to the power b, such that a plus b, it must be 11, and a, it should be less than or equal to b. Only then this 2 to the power a is going to divide 2 to the power b. Now this a, it can take the value 0, 1, 2 up to 5. Now if a is 6, then b will be 5. In that case, x won't divide y. So a can take 6 values. So there are 6 possible ways for 2. In the same way, for this 3 to the power 6, we'll get a plus b equals 6. Again, a is less than equal to b. Now here the value of a can be 0, 1, 2 and 3, which are 4 possible ways. Now a plus b equals 3, then a can take the value 0 and 1, so there will be 2 cases. Now for a plus b equals 2, a can take the value 0 and 1, again 2 cases. Now if a plus b is 1, then a can take the value only 0, and here also it is 1. So it will be 6 into 4 into 2 into 2, which is 16 into 6. And 16 into 6 is 96. So this third case, it matches with R. So this C, it matches with R. And finally, this fourth case where alpha and beta are positive integers and HCF of alpha into beta is 35. So HCF of alpha into beta, it will be 35 when, now this HCF, it can only be 35 if 5 is present in one of the numbers and the other number should have 5 square. And in the same way, one number should have 7 and the other number should also have 7. So one of the number, it will have 5 into 7 and the other number, it must have 5 square into 7, and this can be done factorial 2 ways. Now other than that, nothing should be common. So now we have 2 to the power 11, 3 to the power 6, 11 into 13, and they can be factorized in 2 to the power 4 ways. So it will be 16 into 2, and that is 32. So this D, it matches with P. So A matches with T, B matches with Q, C matches with R, and D matches with P. Now here the question is, a father with 8 children takes 3 of them at a time to zoological garden as often as he can without taking the same 3 children together more than once. Now number of times he'll go is, so number of times he'll go is number of distinct combinations of 3 children. So distinct combinations of 3 children will be simply 8C3, which is 8, 7, 6 and 6, and will be simply 56. So that means this option 1 is correct. Number of times each child will go. Now suppose we have this particular child A, and this child A, it must go. Now this A, it will go with 2 other child. So 2 other distinct combinations from remaining 7 is given by 7C2, which is 7 into 6 divided by 2, and it will be 21. So this option 2, it is incorrect. Now number of times a particular child will not go, it will be simply 56 minus 21, and which is 35. That means option 4 is correct. So the correct options are 1 and 4. Now here the question is, if x, y and z are natural numbers such that LCM of x, y is 2744, LCM of y, z is 1372, and LCM of zx is 2744, then number of triplets of x, y, z is n, where sum of digits of n is. Now we have x and y, and LCM of x, y is 2744, which is 2 cube into 7 cube, and LCM of YZ is 1372, which is 2 square into 7 cube, and LCM of X and Z is again 2744, which is 2 cube into 7 cube. Now since LCM of XY contains 7 cube and LCM of YZ also contains 7 cube, LCM of XZ also contains 7 cube, that means at least 2 of X, Y and Z must contain 7 cube. So these two, it can be either XY, YZ or XZ. So these two, they can be selected in 3C 2 ways. If 2 of them, they are 7 cube, then the third one, it could be 1, 7, 7 square and 7 cube. So it will be 3C2 into 4 minus, now we have 3 cases. Now in each of the 3 cases, we'll have 7 cube, 7 cube and 7 cube. So we have to remove 2 cases from this. So it will be 3C2 into 4 minus 2. So it will be 12 minus 2, and that is 10. So all the possible combinations of 7, it is given by 10. Now we look at all the possible combinations of 2s. Now we have x, y, and z. Now LCM of xy contains 2 cube. LCM of yz is 2 square, and LCM of xz is also 2 cube. That means this x, it must contain 2 cube. Now out of yz, one of them, it must contain 2 square. So suppose it contains 2 square, then z can be 1, 2 and 2 square, or z can contain 2 square and here it can be 1, 2 and 2 square. Now this 2 square, it is present 2 times. So total number of ways of distributing this power of 2 is 5. So total number of ways in which we can choose these triplets of x, y and z will be simply 10 into 5, which is 50, and sum of digits is simply 5. Now here the question is, if alpha is x1, x2 and x3 and beta is y1, y2 and y3 and they be 2 3-digit numbers, then we have to find number of pairs alpha and beta such that alpha can be subtracted from beta without borrowing is 3 to the power p, 5 to the power q and 11 to the power r. Then the value of p plus q plus r is. Now if alpha is to be subtracted from beta without carry, then y1, it must be greater than equal to x1, y2 must be greater than equal to x2, and y3, it must be greater than or equal to x3. Now if we consider this leading case for x1 and y1, then x1, y1, they cannot take value 0. Now if y1 is 1, then x1, it can take only 1. If y1 is 2, then x1 can take 2 values, 1 and 2. If y1 is 3, then x1 can take the value 1, 2 and 3. And if y1 is 9, x1 can take the value from 1 to 9. So number of total possibilities is 1 plus 2 plus 3 up to 9, which is 1 plus 2 plus 3 up to 9, n plus 1 by 2, and it will be simply 45. So there are 45 ways possible to choose x1 and y1, and we can write 45 as 5 into 3 square. Now for this second place, x2 and y2 can be 0. If y2 is 0, then x2, it must be 0. If y2 is 1, then x2 can take the value 0 and 1. For y2 equals 2, x2 can be 0, 1 and 2. And for y2 equals 9, x2 can take the value from 0 to 9. So this is 1 plus 2 plus 3 up to 10. So number of total possibilities is sum of first 10 natural numbers. So it will be 10 into 11 by 2, it will be 5 into 11. So for this second one, it will be 5 into 11 ways. And for this third one also, it will be 5 into 11 ways. So total number of ways possible will be 3 square, 5 cube into 11 square. Now P is 2, Q is 3 and R is 2. Now the value of P plus Q plus R will be simply 2 plus 3 plus 2, which is 7, and that is the answer to this question. Now here the question is, we need to find number of onto functions which are non-decreasing from A to B. Now this set A, it contains 5 elements, 1, 2, 3, 4 and 5. And here we have 3 elements, 7, 8 and 9. Now since the function is onto, that means all the elements, they must be mapped, and it is non-decreasing. That means either it should be constant or it should be increasing. So this 1, it must be mapped to 7, and this 5, it must be mapped to 9. Now we have to map 2, 3 and 4 with 7, 8 and 9 so that this function is onto and increasing. Now this 2, it can be either mapped to 7 or this 2, it can be either mapped to 8. Now if 2 is mapped to 7, then 3 can be mapped to either 7 or 3 can be mapped to 8. And if 3 is mapped to 7, then for this function to be an onto function, 4 must be mapped to 8. So we have this one possibility. Now if 3 is mapped to 8, then we have two possibilities for 4. Either 4 is mapped to 8 or 4 is mapped to 9. So we have three cases here. Now for the second one, when 2 is mapped to 8, then either 3 is mapped to 8 or 3 is mapped to 9. And if 3 is mapped to 8, then for 4, we have two possibilities. Either 4 is mapped to 8 or 4 is mapped to 9. And if 3 is mapped to 9, then obviously 4 will be mapped to 9. So we'll have 3 more cases here. So total number of such functions will be simply 6. Now here the question is, there are n intermediate stations on a railway line from one terminal to another. In how many ways train can stop at 3 of these intermediate stations if the first one is all the 3 stations are consecutive. Now in consecutive selections video, we have studied that from n, if we have to select r consecutive, it can be done in n minus r plus 1 ways. So from n, if we have to select 3 consecutive, so it can be done in n minus 3 plus 1, which is n minus 2 ways. That means option A is incorrect. Now first we look at this option B. No 2 of these stations are consecutive. Now this is non-consecutive selection, and we have studied that non-consecutive selection is given by n minus r plus 1 c r ways. Now here it will be n minus 3 plus 1 c 3 ways, which is n minus 2 c3. Now n minus 2 c3 is n minus 2, n minus 3, n minus 4 divided by 6. Now if we look at this nc3 minus n minus 2 square, it will be n minus 1, n minus 2 upon 6 minus n minus 2 square. We can take this n minus 2 common. It will be n into n minus 1 minus 6 n minus 2 upon 6. So it will be n minus 2 by 6, and here we can write this as n square minus n minus 6n. So it will be minus 7n plus 12, which is 4 into 3. So we can write this as n minus 2, n minus 3, n minus 4 whole divided by 6. That means this option D, it is correct. Now this option C is at least 2 of the stations are consecutive. So that means from total ways, which is nc3, we have to remove all the cases when no 2 stations are consecutive. So we'll remove this nc3 minus n minus 2 square. So this nc3 will cancel. So it will be simply n minus 2 square. That means this option C is also correct. So the correct options are C and D. Now here the question is, Tom has 15 ping pong balls, each uniquely numbered from 1 to 15. He also has a red box, a blue box, and a green box. So we have distinct balls and distinct boxes. The number of ways Tom places 15 distinct balls into 3 boxes so that no box is empty is 3 to the power 15 minus 3 into 2 to the power 15 plus 3. Now this is nothing but this is number of onto functions defined from 1 to 15 to 1 to 3. So number of onto functions it is given by, so for each of these 15 balls we have 3 choices each. So total number of choices will be 3 to the power 15 minus all the cases where at least one box is empty. So for this first one it will be 3C1. Suppose red box is empty. So for these 15 balls we have 2 choices. So it will be 2 to the power 15 and then minus any 2 boxes which are empty. So it will be 3C2, and all these 15 box they'll go to this remaining box. So it will be 3 to the power 15 minus 3 into 2 to the power 15 and plus 3. That means this option A is correct. Now option B is, Jerry also has 15 ping pong balls, again distinct, and he also has 3 boxes, red, blue and green. Now suppose that Jerry has placed 5 ping pong balls in each box. Then number of ways, he chooses 5 balls from these 3 boxes so that he chooses at least one from each boxes 2 to 50. So we have 3 boxes, red, blue and green, and each of them have 5 balls. Now we need to select 5 balls so that at least one ball is selected from each box. So it can be 3, 1, 1 or 2, 2, 1. Now first we'll select the box from which we'll draw these 3 balls. So it will be 3C1, and from this box we have to select 3 balls. It will be 5C3 into 5C1 into 5C1 plus, now for this one we'll select this one box where we'll draw this one ball. It will be 3C1 into 5C1 and then 5C2 into 5C2. So it will be 3 into 10 into 25. Now this is 3 into 5 into 10 into 10, which is 750 plus 1500, which is 2250. That means this option B is also correct. Now option C is number of non-decreasing functions. So number of non-decreasing functions, it is given by m plus n minus 1 Cn, which is 5 plus 3 minus 1 C3, and there will be 7C3, and 7C3 is 7656, it will be 35. So that means this option C is also correct. And then A is 1, 2, 3 and B is 1, 2, 3, 4, 5. Then number of functions satisfying fi unequal to I is 64. Now for this one, it cannot take the value 1. It can take any one of 2, 3, 4, 5. So we have 4 choices. For this 2, again we'll have 4 choices, and for this 3 also we'll have 4 choices. So total number of choices will be 64. That means this option D is also correct. So the correct options are A, B, C, D.